We've already talked about p-values, but they're so incredibly important that I wanted to take a break and just devote a little bit of time specifically to these things. Again, the p-value is the probability of observing something as strange as what you actually saw given the null hypothesis is true. Or more specifically, it's the chance of observing a value of the test statistic that's at least as extreme as the one that we observed from our sample. So if you think about doing a right-tailed test for a mean, then the p-value is just the chance that this test statistic, and this t here, that's just my little shorthand notation for, what is the test statistic there? You take the sample mean, the random sample mean, and you standardize it, right? According to, if the null hypothesis is true, then the true mean there is mu naught. And I divide by s over root n, right? And according to William Gossett, aka student, all of this stuff, which I'm just abbreviating all that stuff with the big T there, it behaves according to a T distribution within -1 degrees of freedom. So if you're doing a right-tailed test, the idea is, you find this T number, this test statistic, and then you would shade the area off in the right tail. If you're doing a left-tailed test, then again, what is that? That's when your alternative hypothesis is of the form that mu is less than mu naught. If you're doing a right-tailed test, that means your alternative hypothesis is of the form mu is greater than mu naught. If you're doing a two-tailed test, it means that your alternative hypothesis is of the form mu is not equal to mu naught. For a right-tailed test, the p-value is the area up under that t-curve to the right of your test statistic. For a left-tailed test, the p-value is the area up underneath that t-curve to the left of your test statistic. If you're doing a two-tailed test, you calculate the value of your test statistic, take its absolute value, that'll make it positive, right? Sends it over here, and then you find that area and then multiply it by 2. Okay, you just pick up twice the small tail area. That's how that works, because you're essentially wanting to know what's the chance that you would observe something as extreme or more extreme off in either direction. Now, I want to talk just a little bit more generally here, because this notion of p-value is all over the subject of statistics. It doesn't matter if you're doing a hypothesis test for a mean or a proportion, or if you go on to take more statistics, and I sure hope you do, you might see something strange like this. Maybe the null hypothesis is the median takes on the value of, say, 9.6, and the alternative is that, say, the median is less than 9.6, okay? Or you might have something like this. The null hypothesis is that the mean for this group is the same as this group over here, which is the same as this group over here, and on and on and on. You might have several different groups, and you're wondering if their means are all equal. And maybe the alternative hypothesis is that something like at least one of these means is not like the others. It doesn't matter. There are many, many, many kinds of hypothesis tests in statistics. Sometimes we even have hypothesis tests about variances or standard deviations, like, the standard deviation for one group is equal to, say, the standard deviation for group 2. And maybe the alternative hypothesis is no, that maybe they're different. Sometimes you want to check to see if the spread outnesses of distributions are the same or different. But regardless of whatever kind of test you're doing, it always boils down to, number one, there's some meaningful test statistic involved in testing this thing. And number two, under the null hypothesis, something about how that test statistic should be behaving. Okay? It may be sort of bimodal like this. Okay? Or it may be that the test statistic is behaving very right skewed. Okay? Test statistics do not have to have a nice symmetrical shape like a bell or one that resembles a t-curve. But the idea is always the same. The p-value is always the chance that that test statistic would hit as extreme or more extreme off in the direction as prescribed by your alternative hypothesis. You're essentially evaluating how unlikely this so-called outlier is. Okay, how do you check to see if this thing, if something's an outlier? Well, is it very far away from the rest of the pack? Well, one way to measure that is how much area is left off here in the curve. If there's just a little itty bitty bit of area out there all the way out to the right, then that's pretty far off to the right, right? Right. Similarly, if I have a test statistic that's behaving this way, okay, and if I actually observe the test statistic and it's here, well, that's not so strange, right? But if it lands over here, and then that's pretty abnormal, right? Because this area over here is pretty small. My point here is that it doesn't matter what kind of hypothesis test you do in statistics. It always boils down to, number one, writing out your null and alternative hypotheses. Number two, checking your assumptions. Number three, there's some meaningful test statistic such that if the null hypothesis is actually true, then you know how that test statistic should be behaving. And number 4, you go and you gather some data, compute the test statistic, and if it's far out in one of the tails of the distribution in the direction of the alternative hypothesis, then you reject the null in favor of the alternative.